So I'm going to talk about automatically discovering geometry theorems, something you might want to do if you wanted to pose a proof problem that the solution didn't exist on the internet, or one might want to do to automatically provide test situations for a symbolic geometry program. Specifically, I'm going to talk about angle theorems, and even more specifically, I'm going to talk about angle bisector theorems. Now, that's not quite as small a universe as it would initially seem. For example, the theorem there, although it only has one explicit angle bisector, it has a reflection, which, when you think about it, reflection specifies that the mirror is the angle bisector of the incoming ray and the outgoing ray. And it also has a circumcenter, which defines three isosceles triangles. And the isosceles triangle, the base is perpendicular to the angle bisector at the apex. So this is, in fact, an entirely angle bisector theorem. I'm actually going to represent angles in terms of the directions of directed lines, their angle from the positive x-axis. And so the angle between two such lines is just the difference in their directions, as long as the positive x-axis doesn't lie in the angle. If it does, it's that difference plus 2 pi. Now, this need to remember where the positive x-axis is makes this a very poor representation for human beings to use, but computers can be coerced to deal with it. I define the principal angle bisector between two directed lines to be the line which has a direction, the average of the two directions. And this is going to be in the sector that does not contain the positive x-axis, which may, of course, be a reflex sector. If you have an isosceles triangle, the base is just pi by 2 away from the angle bisector. The angle bisector has, of course, satisfies the equation alpha plus beta minus 2 gamma equals 0. That's just expressing the average. The base of the isosceles triangle has that same equation, but with a pi or a minus pi, depending on which direction we're regarding it, on the right-hand side of the equation. So here is a pure bisector theorem. We have V5 is the bisector, angle bisector of V1 and V2. And we can see contributes the equation over there on the to the right there. V6 is the bisector of V2 and V3, contributing that equation. V7, bisector of V3 and V4. V8, the bisector of V1 and V4. Now, because V1 and V4 has the positive x-axis between them, then that V8's in, as you can see, is in the reflex sector. V9 we're defining as the bisector of V5 and V7. And we're going to make a final statement, which is that V9 is also the bisector of V6 and V8. So those 6 linear equations can be expressed as a matrix equation. If we look at the rank of this matrix here, we find it's rank 5. It has 6 rows, so that says we're rank deficient, which means that the 6th row could be defined by the previous 5. That is that this is a theorem, that 6th row is determined. So if we think in terms of isosceles triangles, we're going to get a couple of differences. One, we're going to have something other than 0 on the right-hand side. There's some pi's and minus pi's distributed there. But also our 2 final bisectors are clearly not pointing in the same direction. So I've separated them out. I've got W9 and W10. W9 is the bisector of W5 and W7. W10 is the bisector of W6 and W8. And I've created an equation that says they're a specific angle, actually pi by 2, apart. So we end up with a matrix which has, if you notice the difference, I've split the final column into 2, but I've added an extra row for the angle, but that still has a rank 1 less than it ought to have, as rank 6. So the final row is determined, and we have a theorem. So that was, if you like, a little tutorial about looking at these equations, these theorems as matrices here. I want to go to where I started with this little project. I started with a couple of different theorems, both of which are bisector theorems. The first was this theorem where we have two cyclic quadrilaterals which share 3 of their sides. The theorem states that the fourth side of each, FG and DE, are parallel. So I can break these this into 8 isosceles triangles and come up with the matrix. So for example, I have an isosceles triangle 1, 8, 12. And over here in matrix, I've got a line with 1, 8, 12. I have called FG and ED the same thing. They're both direction 12 because they're going to end up being, we want them to be parallel. So they both have the same direction. So they're both occupying this 12th column of my matrix. And that matrix is rank deficient. It has rank 7. Here is the other theorem I was thinking about. In this one, we have a hinged mirror ABC, and we're impinging 2 parallel rays on that, A and C, and the reflected rays meet in a point which lies on the circumcircle of A, C, and O, where O is the circumcenter of A, B, and C. Now, this has got a lot of isosceles triangles in it, but it's also got a couple of explicit reflections. So I've called the 2 parallel lines both 12, and we see that 12 reflects in AB, reflects in line 1 to give me 8. And so that contributes the line of the row of my matrix with 8, 12, and 1. And likewise, 12 reflects in 10 to give you 7. And that gives me the final row, 12, 7, and the bisector is 10. Now, when I looked at these matrices, both have rank 7, so both reflect, both are theorems. But when I looked at them, I noticed that the non-zero entries are in the same place. Of course, that was fortuitous labeling on my part, but I did collaborate to create these. So I was thinking, okay, what I want to do, of course, is come up with new theorems. So if I could start with another matrix that's rank deficient, I could then work out a way of creating a theorem for that. And I thought, well, I've got 2 with this pattern that are rank deficient. How many others could I get? Well, how many such matrices are there? There's only 3 to the 8. How many? You have to put the -2 into, somewhere on each row. So that's only 6,000 odd. I easily crank that into Mathematica and calculate the rank of each. How many of those have rank 7? The answer is 33. I thought, okay, great, 33 matrices, 33 theorems. Then I thought, well, wait a minute. Maybe they're not all really the same because I can change the labeling of things, and maybe those 33 are just my 2 in different guises. So I wanted to actually look at the 2 matrices in some visual form to give me an idea about that. So visually, sure, every row has got 3 non-zero elements by definition. It's got a 1 and 1 and a -2. But these two theorems both fortuitously, or both have exactly two non-zero elements in every column. And so I thought, okay, that's something that could be represented as a graph where the non-zero elements represent edges of the columns of my matrix represent edges of the graph. So I create a graph with 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 1, 6, 2, 5, and so forth. And that's what it looks like. I'm looking at a cube. But I want to see the matrix represented graphically, so I need to indicate where the -2 is on that cube. And so what I did was I decided that the -2 is going to be in a row and a column. The row represents vertex of the matrix, the column an edge. So I'm going to put an arrow on the edge next door to the vertex that is the row and column. So for example, in my matrix, I have a -2 in the 4, 4 location. So next to vertex 4, on edge 4, I put a -2. And here I also have a -2 in the 5th row. And so next to vertex 5, on row 4, I put an arrow. There's going to be an arrow next to every vertex on one of the edges. Second Theorem's matrix looks like that. And so if I look at them both at once, I can see they're clearly not rotated versions. These are two quite different, different patterns. We can also see that the first one, there'll be 3 potential rotations. And the second one, if you think about it, there's 12. So I've actually got 15 of my 33 right here. But we can, in Mathematica, I can use the graph automorphism group of the graph to find all the duplicates and weed them out. The end result is I have 4 different matrices, different rank deficient matrices based on the cube. Okay, well, I've got two new theorems I can generate. Here's a theorem based on that one, and here's a theorem based on that one. But I want more than 2. So I thought, right, where can I find other rank deficient matrices? And let's work by analogy. I thought, well, let's think of matrices which also have a graph sitting behind them. I know that I'm going to have 3 elements per row. So the graph that I'm going to use is going to have to be uniform degree 3 or cubic. And these are well studied. On 8 vertices, I have 5 connected cubic graphs. So it was an easy thing to go in and just run my program, find all the possible -2 locations for these different graphs. And here's how many I found. None, none, 33, none, and none. So I thought, well, why? That seems odd. Well, it turns out that a matrix with an underlying connected graph is rank deficient if and only if the matrix corresponding to any graph cycle has 0 determinant. And so you can order your rows and columns so the cycle's determinant looks like that. And so just thinking about how you used to compute determinants when you did them by hand, it's going to be that one times the determinant of this thing. So that's the product of all the A's. And then plus or minus, depending on how many you have to count along here, this one times the determinant of this thing here, which is the product of all the B's. So if n is even, the determinant is the difference between the product of the A's and the product of the B's. If n is odd, it's the sum. And with values 1, 1, and -2, you cannot have n odd and a 0 determinant. So we can't have odd cycles, and even cycles have to contain the same number of -2s among the A's as among the B's. So graphically, that gives us this. For a rank deficient bisector matrix, we need the graph has only cycles of even length, which is called a bicubic graph. And if you traverse any cycle, you encounter as many arrows in your direction of travel as going against it. So every time you go against an arrow, you add one. Every time you get one going with you, you subtract one, and you have to add up to 0 as you go around the arc. And you can verify that all 4 of those graphs have that property. So I need to look at other numbers than 8 if I want more rank-deficient graphs. But I know I need to look for bicubic graphs. 4, there are no bicubic graphs. 6, there is one bicubic graph, and it yields these 2 rank-deficient matrices. 10 has 2 bicubic graphs, and it yields 19 rank-deficient matrices. 12 has these 5 bicubic graphs, and it yields 146 matrices. 14 has 13 bicubic graphs and yields 807 matrices. Now, the problem is once you get up to 13 or 14, you're getting rather complicated theorems. There's quite a few lines. But you can simplify the theorem. Once you've got the complicated theorem, you can simplify it by merging lines. So, for example, this theorem we started with can generate this other simpler theorem by merging line 1 and 8, then line 12 disappears, and we end up with the combined line 1 and 8 being perpendicular to the baseline. In a similar fashion, a theorem derived from this 10-row matrix, which is not too complicated, but it can be simplified by initially merging the isosceles triangle ADL into a single line and give us this second theorem. And then that third one can be created by merging the 2 red lines, give us this one here. So the complicated ones can be made reasonably simpler. So I'm interested in generating new geometry diagrams, so I want to go from matrix to geometry. This matrix obviously creates this piece of geometry, but you can reinterpret the bisectors in different ways to get different forms of the same theorem, reinterpreting them as pure bisectors, as reflections, as cyclic polygons, and so forth. However, my program is only going to choose one method, so all the theorems are going to look somewhat similar. What I'm going to do is I'm going to aim for cyclic polygons from the get-go. They're useful because you can throw away all the spoke lines and make them implicit, and so it keeps the clutter down. So the process looks a bit like this. We start with one of the matrices. I identify cycles or even paths of sides which don't have any arrows on them. These are good candidates for spokes of a cyclic polygon. The neighboring edges on the graph become the sides of the cyclic polygon, and any shared sides like we have here and here become parallel constraints between the sides of the cyclic polygon. And the final edge in this one is now states that the final 2 bisectors are the same. Well, the same as long as you treat the same as meaning they have a fixed angle between them, fixed angle in this case, pi by 2. So here's what it does in code. My program, which first of all, it's going to create a little description, a little neutral description of the theorem. It sends that in to get a textual description minus the conclusion. We then get a graphical form in the form of a geometric scene with the conclusion in red. We still don't actually have a value to the conclusion. We now create a geometric instance of that. And from the geometric instance, I can actually extract what the conclusion is going to be, L2 is perpendicular to L1. In some cases, the conclusion actually depends on the instance and not on the geometric scene itself because of the location of where that x-axis is, and so such like. Actually, it's not quite that. Right. So random theorem generator just picks a rank-deficient matrix at random, randomly merges pairs of columns, interprets that as a theorem, creates a statement without conclusion, creates a diagram, abandons the example and starts again if this step takes too long, which it sometimes can, and then measures the conclusion angle from the diagram and completes the statement. Here is a result of a run of this generating a bunch of theorems. Here's one that is generating a perpendicular. Here's one that generates a pair of parallel lines. It doesn't have to be perpendicular parallel. We'll see in this one it's 67.5 degrees. That is, of course, 3 pi by 8. It will have to be a binary rational of pi. This one is 45 degrees. And some of these clean up quite nicely. Let me show you that one. Expressed in terms of parallelograms and rectangle. That's a reasonable little theorem you might ask somebody to prove. Here's another one of the ones that came out of that run, cleaned up, where you're asking for an angle with a couple of parallelograms intersecting a circle. My personal favorite from that run is this one, which starts with a general triangle and ends with a specific triangle. But unlike Napoleon or Morley or those guys, my specific triangle is not an equilateral. Not even Isosceles, and not even got a single 90-degree angle in it. However, it is determined by the construction. So at that point, I'd like to stop. I put the software, the functions on the functions attached somewhere to the presentation. I'll just run it in case anyone's got any questions. We can actually get the excitement of seeing a new theorem popping up in front of us. So have a go with it if you like. It takes a couple of parameters. The second one is how long you're prepared to wait for for the. There we go. It did generate a couple of theorems. And that looks yeah, it's quite a fun thing. Watch these things come out and see if you can find ones which you can express in a somewhat simpler, nicer way. So I will say thank you at that point and stop. Thank you.